Carbon-14 has a half-life of 5,715 years. We have a fossil which has lost 75% of its original carbon-14. How old is our fossil, and how much carbon-14 will remain when the fossil is 50,000 years old? So this is a radioactive decay problem. Okay, the tip-off is half-life. So we write down our equation. That's going to be A of t equals A0 times e to the constant c times t. Our constant c, when we solve for it, will be a negative number. As time goes on, we're going to want our amount to get less and less. So that's the whole point of decay. Now, let's focus on half-life. What does half-life mean? That means if I start out with A0, when one half-life passes, the amount that will be left is 1/2 A0. So in this case, when 5,715 years pass, if I start out with A0, we get 1/2 A0. Using the equation though, we'll also get A0 times e to the c 5,715. Okay, we can cancel the A0s. That leaves 1/2 e to the c 5,715. We want to take the e out. So to do that, I apply natural log to both sides. Natural log of e to anything returns your anything. On the other side, we'll have natural log of 1/2. But if I write 1/2 as 2 to the minus 1, we could bring the minus 1 out in front of the natural log. So at the end of the day, we'll have c equals minus natural log of 2 over 5,715. Now, let's take c, put it back into the original equation. I do that. We could separate out the minus t over 5,715 to the outside of the parentheses. On the inside, I'll have e to the natural log of 2. That simplifies to 2. E to the natural log of anything collapses. And then I have my final equation, A0, 2 to our exponent here. Now, we can answer some questions. The first one, we've lost 75% of our original sample of carbon-14. That means we have 25% right now. So if we start with A0, we now have 0.25 A0. We're going to set that equal to our equation, and then we're going to solve for t. Again, the A0s cancel. I could rewrite 0.25 as 1/4 or 2 to the minus 2. And then you note I have an equation where we have two things are equal. They have the same base. That means the exponents have to be equal. Another way to think of that, you can apply log to the base 2 to both sides. Log base 2 to the 2 to the anything cancels to leave us with anything. That leaves me with minus 2 equals minus t over 5,715. Clearing the denominator gives me t equal to 11,430 years. So that's how old the fossil is. Now, we can check that. That's exactly 2 half-lives. So let's see what happens. If I start with A0, 1 half-life passes, we cut the original amount in half. Another half-life passes, we'll cut this amount in half, and you note we have 1/4 of our original amount. So that means we have 25%, just like we started with. So our check works. Second, we want to know how much carbon-14 is left at 50,000 years. We put that into our equation. That's going to give me A0 times 2 to the minus 8.75. Now, in our final answer, we won't want an A0 in there because we didn't start with an A0. So we'll just give our answer as a percentage of the original amount. So when we crunch this down, we get 0.0023 A0. We're divide that by the original amount, which is just A0, and then multiply by 100%. So our answer is going to be 0.23% of the original amount of carbon-14.